Multiple scattering. So far we've just talked about scattering from a single interface. In this lecture, we're going to generalize that discussion by talking about what happens when there's multiple interfaces. And then we'll apply that to an anti-reflection layer and a Bragg grating and explain some other things. Let's look at scattering from a dielectric slab. So here's our setup. We have a dielectric slab. Here we're calling it medium 2 because before that we have a medium 1 that extends out to minus infinity. And on the other side we have medium 3 that also extends out to positive infinity. So our dielectric slab here has refractive index N2, impedance eta 2, and a thickness of D. So now we want to ask ourselves what happens when a wave encounters this setup that has two interfaces. So we apply an incident wave, and we'll let it have an amplitude of E0. Well, we know from our previous discussions when a wave hits an interface, two things happen. Some of it reflects and some of it transmits. So that's exactly what will happen. So if we have medium 1 and medium 2, we can quantify the local reflection coefficient here as an R12. So what gets reflected off of this interface due to this applied wave is R12 times E0. That means whatever gets transmitted across the interface is a T12 times amplitude E0, where this is the local transmission coefficient. So then what happens? Well, this transmitted wave propagates itself all the way across the layer to the other side. When it does that, it accumulates a certain amount of phase. And for right now, let's just characterize this phase with an e to the minus j phi, where somehow the thickness and wavelength is lumped into this psi parameter. And we'll get to that in a little bit. So now the wave encounters this second interface. Again, two things happen. Some of that can reflect, and some of that can transmit. The amount that reflects, if this is medium 2 and medium 3, will have a reflection coefficient R23 times this whole expression. So it's an R23 times T12 times amplitude E0 times this complex exponential e to the minus j psi. And then what gets transmitted? It's a transmission coefficient T23 times this expression. Now we have this reflected wave, which then propagates backwards through the layer. So all that happens here is it accumulates another e to the j phi of phase, giving us a total of e to the minus j2 psi of phase. I think I just called it phi and I meant to say psi. So it accumulates another e to the j psi phase, leading to a total of e to the minus j2 psi. Now we have this wave incident on the first interface, but in the reverse direction. It's going from medium 2 to medium 1 now. So some reflects, some transmits. To characterize the transmission, now we have a T21, indicating that the wave is transmitting from medium 2 to medium 1. The rest of the expression is our incident wave. And what gets reflected? An R21, which is different than the R12. R12 was for our wave going from medium 1 to medium 2. Now we have a wave going from medium 2 to 1. So we have an R21 here. And the rest was our applied wave at this interface. So this reflected wave then propagates across our layer, accumulates yet another e to the j psi phase. So we have a total of e to the minus j3 psi phase. That wave reflects and transmits. We tack on a reflection coefficient and a transmission coefficient. This reflected wave backward propagates, accumulates another e to the minus j psi phase. So we have a total of e to the minus j4 psi. Some of that reflects, some of that transmits. We tack on a T21 transmission coefficient, another R21 reflection coefficient. Since we already had one there, now we have an R21 squared. Of course, that wave backward propagates. and reflects and transmits, and backward propagates and reflects and transmits. And this goes on to infinity. And so in fact, we get an infinite number of reflected waves, and we would add all of them together to get total reflection. We also get an infinite number of transmitted waves, and we would add all of them together to get the overall transmission. Now let's look at what's going on just at the interfaces. So we have these little local reflection coefficients. We have an R12 for a wave traveling in medium 1, incident on medium 2, reflecting backward this way. We have an R21 for a wave in medium 2, incident on medium 1 that reflects. We have our transmission coefficient, T12. That's for a wave in medium 1 passing into medium 2. And since we already have an expression for R12, we can use our equation that related the transmission and reflection coefficient. And also the same thing for T21 for a wave traveling backward. Now this psi term, which is talking about phase, that's K0 times refractive index times the thickness D. This is the amount of phase that a wave accumulates through one pass of that dielectric slab. Now on this other side of the interface, we have an R23. That's a reflection coefficient for a wave going from medium 2 to 3. And we don't need an R32 because there are no backward waves coming from medium 3. And likewise, we only need a transmission coefficient T23 that we calculate from R23. These are just the little local reflection and transmission coefficients as if this was just a single interface. Likewise, these are just local transmission reflection coefficients as if this interface were just a single interface. Now we want to tie all of this together. Before we do, let's just make some generalizations that we won't get into. What we just analyzed was for normal incident and no loss. And this is our psi term describing how much phase is accumulated. Now, if that wave comes in at an angle, everything we're going to do is still valid. We would just calculate psi differently, and we would incorporate an angle here. The steeper the angle coming in, the more phase it accumulates through the thickness of the slab, simply because now it's traveling at an angle and takes longer to get through the layer. Now, if we have a lossy medium for our dielectric slab, we use a complex refractive index. We're in the negative sign convention, so we express our complex refractive index this way with a minus sign. And if it's lossy and we have an angle of incidence, we'll use a complex refractive index and a cosine here. But for our examples, we're just proceeding with the normal incidence no loss case. But the only difference between what we're deriving and what you'd have to do for these more general cases is just replace what psi is. Okay, the overall reflection. We get an infinite number of reflected waves. And so we write them down. This was our initial reflected wave. This was our reflected wave that went through the slab and back again. This is our reflected wave that went through the slab, back again, through the slab, and back again. And so on. And this repeats. And there's an infinite number of terms. So anytime we have an infinite number of terms, we can write this as a summation. And if we stare at it long enough, we can realize other than this term, we have to leave that to the outside. All the other terms have or look very similar, and we can write it in this form, with an n being which reflected wave we're talking about from 0 to infinity. There's an infinite number of reflected waves. Now in this summation, we can factor out some terms that don't have n in them. We're left with this expression to the n power. And the whole reason we did this is this will turn out to be a geometric series, which lets us replace the summation with a closed form equation. But all we've done to get there is just factor out some terms that didn't have n in them. So our overall reflection is this R12 plus our summation, which has the infinite number of waves. Let's keep going. This is a geometric series. Any summation that goes from 0 to infinity that has some constant multiplying a variable, call it x, to the n power, and as long as the magnitude of this number x is less than 1, this series is guaranteed to converge to this. And it turns out we have a geometric series, and reflection is always less than 1, so our x in that case will satisfy this condition, and we can replace our summation with that equation. That will let us simplify things down. So here's the reflection equation we had from the previous slide, and if we look at this summation and this summation, we can see, yes, we do have a geometric series, and we're guaranteed that what's inside these parentheses is less than 1 because our reflection coefficients, their magnitudes, have to be less than 1, and this complex exponential can never be greater than 1. So we're guaranteed to have this be less than 1. That means we can replace our summation with what happens to a geometric series, what it converges to. So our summation is gone. That's awesome, but we're still accounting for an infinite number of reflected waves. So we can bring this expression into the numerator, and now we have a new expression for overall reflection. We still have some work to do. So we had a lot of different terms in there that came from these local reflections and local transmissions. Well, it turns out R21 and R12 really are the same number, just with a negative sign. So in fact, we don't have to keep R21 in our equation. We can replace it just with minus R2. Likewise, we can replace T12 with a 1 minus R12. So again, we're putting things in terms of just R12. We're eliminating variables. We can put T21 in terms of R12. And we can put T23 in terms of R23. So there's the expression we had from the other side. And so we'd come across a term like, let's say, T12, and we're going to replace that with 1 plus R12. So let's go ahead and replace everything that we can. And now we end up here. We have fewer variables. So we can multiply all of that out and simplify a bit, and we end up here. And that is our final reflection and the most general equation for reflection from a dielectric slab. So even though we're still using this little r, make no mistake, that is not a reflection from a single interface. This is the reflection coefficient from the slab, where we had two interfaces and an infinite number of waves bouncing around and reflecting and transmitting. Let's do the same thing for the transmission coefficient, although the steps are the same, so we can do this in a bit more abbreviated manner. But we write all of the terms from our analysis of what got transmitted. We recognize that we can write that as a summation. We factor out terms to put the transmission coefficient in the form of a geometric series. Not all of it's in the form of a geometric series, but the summation that's left over is definitely a geometric series, which we can then replace with what the geometric series converges to. Then we can replace all of our little variables with just R12 and an R23. So there's our expression we had from the previous slide. We replace all of our variables, and we end up here, and that is our final and most general expression for the transmission coefficient through the dielectric slab. And I'll remind you again, even though we write this as a little t, make no mistake, this is not a transmission coefficient through just one interface. That's through the whole thing where we have all these waves bouncing around, and it leads to this different type of transmission coefficient that arises from multiple scattering. So it turns out we can derive a relation between R and T. So we start off with the expressions that we derived for R and T. Notice they have the same denominator. So let's solve both of those equations for the denominator. So now, since we've solved for the denominator, that has to mean what's on the right-hand side here has to equal what's on the right-hand side over there. So we set those equal, and we simplify. And we have an expression that relates our transmission to reflection through this dielectric slab. So that is not the same relation that we saw for a single interface, because we don't have a single interface. We have two interfaces, and we have an infinite number of waves bouncing around here. Let's plot this as a function of wavelength. And really, these dielectric slabs can operate in one of two regimes. If the reflections are very small, say 10% or less, it turns out the reflection and transmission, if we were to plot them, follows something very close to a sine or cosine. Now, if we have very strong reflections, let's say 90% or greater, instead of having sine waves, we have impulses almost, and it resembles very much a comb filter. This is used a lot in lasers, where we want to lock a laser, we want to put a mirror on either end, and we want to filter as tightly as possible. And so they'll cap the end of laser cavities with rather strong mirrors that have at least a 90% reflection, and it turns out that laser cavity will only laze over a little tiny line width. So that's one area where this is applied. So anyway, if the response of your dielectric slab is sharp little spikes, that means we have strong reflections off of those interfaces. If it looks more like a rolling sine or cosine, that means we had weak reflections. And it's not a sharp cutoff between the two. As the reflectivity of those interfaces goes up, it kind of transitions from one to the other. So let's derive the low finesse case, meaning we have very low reflections, and let's see how just this sine or cosine response falls out of it. So we have our reflection and transmission. Now, to make this simpler, let's assume we have a symmetric slab. So that means our R12 will be minus R23, and we can reduce the number of variables in our equation. So we go ahead and we do that. Then we multiply everything out, and we end up here. Now notice, we have the same thing in the denominator, but for small reflections, something that's very, very small. That means this R is small, and we're squaring it, so it's going to be even smaller. The biggest this exponential can be is 1, so that has potential to make this even smaller yet. So the reality is it's just 1. It's approximately equal to 1 when R12 is itself small. So that means we just have 1 in the denominators here, and our expressions for RT reduced to that. So we have now very simple equations for the low finesse case, where we have very weak reflections at the boundaries of our slab. Well, we still don't see that sine and cosine yet. So what we want to do is look at the magnitude of this. And if we calculate the magnitude of our expression for the reflection, now we see this sine come out. And we see that this sine is a function of the phase through the slab. So that means as we change refractive index or change the thickness of the slab, our reflection will go up and down. And in fact, as we were to stretch our cavity back and forth and we watch reflection go up and down, those are called interference fringes. And this is really how they have measured gravity waves. They interfered light. And gravity was warping space-time and changing the length of interference cavities, and they were looking at the light go bright, dark, and counting those fringes. So it's actually a really sensitive phenomenon, and they can make interferometers that are hugely, hugely sensitive. This type of interferometer is something called a Fabry-Perot. I believe they use a slightly different type for detecting gravity, but it's based on the same principles. Let's do an example. And let's answer the question, do windows block Wi-Fi? Well, windows are usually made of fused silica, so it has a refractive index about 1.52, and they're about 3 millimeters thick. Now that we can calculate reflection and transmission through a dielectric slab, let's see what the transmission through a plate of glass is at Wi-Fi frequency, which is 2.4 gigahertz. So we pull up our transmission equation, and we calculate all the different variables we need. We can convert our impedance to refractive index so that we can calculate our reflection coefficients. So our reflection from air to glass is about 0.2. We've even seen that before. Our psi term, the phase through one pass through the glass, K naught, refractive index D, is about 0.229, and this is in radians. Now that we have those numbers, we can plug those back into our transmission equation. So we plug in the numbers, and we get this value. We really would like to look at how much power gets through, so we take the magnitude and square it, and we see that 99.5% of Wi-Fi gets through your window. So the conclusion is windows do nothing to block Wi-Fi. So your Wi-Fi signal will get through windows. You don't have to worry about that. Here's another example that's pretty neat. If you put oil and water, you see rainbows. And if you move your head up and down, you'll see those colors sort of change. That's called iridescence. Well, there's no rainbows in oil. There's no rainbows in water. What's happening when you put oil and water? Well, you're actually getting a thin film here. It's a dielectric slab. And the reflectivity off of this is a function of this angle of incidence. And so as you're looking out over the water, as you look out farther or closer in the water, you're essentially looking at different angles. And so you're seeing the different colors. That's also why when you move your head up and down, those colors look like they change, and that's called iridescence. So oil and water is a great example of a dielectric slab, and a pretty neat one that we're all familiar with. Let's look at an actual application, something called an anti-reflection layer. So suppose we have the interface between two materials, material 1 and material 2. Since there's a change in impedance, we will get reflections. Well, if we're designing something, sometimes we don't want that reflection. For example, a camera lens. So now we have light going from air into the glass of the lens. We don't want that light to reflect. We want all of that light to go through the lens and make it to our detector. But light always reflects off of glass. What can be done? Let's insert a dielectric slab between those two layers. And then if we choose everything just right, hopefully we can prevent reflections for a wave going from material 1 to material 2 by injecting this third layer. So let's figure out how we can design this. And what we'll do is we'll go back to that equation, the calculated reflection through the dielectric slab, and we'll ask that equation, what can we do? And we'll derive some rules from that. So that was our most general expression for reflection from a dielectric slab. We want the reflection to go to 0. And so that's controlled through the numerator. In order to get reflection to be 0 with the denominator would have to approach infinity, and that can't do that because our reflection coefficients have a maximum value of 1. Our complex exponential has a maximum value of 1. So the biggest value really that we can get down here is 2. So it has to be the numerator going to 0 that will get the reflection to go to 0. So we grab the numerator and set it equal to 0. Now the reflection coefficients R12 and R13, they arise from the materials in our problem. We really can't adjust those. So what is it that we can adjust? The only thing left there is that theta term, the e to the minus j2 theta. So let's solve this equation for the e to the minus j2 theta term. When we do that, we get this. Then we want to solve for theta. So we do that by taking the natural log. When we take the natural log, we actually have to add in here this minus integer multiple of pi. That's very important because this complex exponential is like a sine or a cosine function. I could add or subtract an integer multiple of 2 pi radians to that and get the same answer. So if I take the natural log, it's not proper just to write that as e to the minus j2 theta. It's e to the minus j2 theta plus or minus an integer multiple of 2 pi. So anyway, we solve that for theta and we end up here where m is just any integer. Let's keep going. So the reflection off the first interface is the impedance of our anti-reflection medium, which we don't know yet, minus the impedance of medium 1, which is fixed. We can't change that. And then divided by the sum of the two. Our 2,3 is the impedance of the second medium. We can't change that. That's fixed and should be known if we're doing this design, minus the impedance of the anti-reflection layer that we don't know yet. We're trying to find that, and divided by the sum. So now we have expressions for those reflection coefficients in terms of the impedances. Let's throw those back into the equation. So now we have this theta term as a function of our impedances. Well, this theta, that was essentially our psi, and that was the phase through one pass through the dielectric slab. That was K0 times the refractive index of the anti-reflection layer times its thickness. So we replace theta now with K0 ND. So now we would like to solve this equation for D. We also want to recognize that K0 is our free space wave number, so it's 2 pi divided by wavelength. And so now we solve our equation for D, and in fact, that is the most general equation that you'll only see here. I don't think you'll see this anywhere else, but that's how we'll calculate the thickness of this intermediate layer given the impedance and the refractive index of that material. So we can go pick a material off the shelf somewhere, figure out what its impedance and refractive index is, and then we can calculate the thickness such that if we inserted that thickness between medium 1 and medium 2, reflections would go to 0. So this is the most general case, and it gives you a lot more options than the equation we're about to derive, which is the equation that the rest of the world really uses. If you Google anti-reflection layer or quarter wave layer for anti-reflection, that's what you'll pull up. Not this equation, but this equation shows us that there's more degrees of freedom that we could potentially use. So this is a big ugly equation, and it has this expression of impedances. So what I do is multiply this out. And then we ask ourselves, what can we do? What simplifications would simplify that? Well, what if we set the impedance of the anti-reflection layer squared equal to eta 1 times eta 2? If we set those equal, then this term minus that term would go to 0. We'd be just left with these center terms. These two terms would cancel, and we would just be left with the ratio, this ratio right here, which is actually just 1. So this entire expression of impedances becomes just -1 when we set the impedance of the anti-reflection layer to the product of eta 1 times eta 2. So since all of this stuff was inside of a natural log and it is -1, natural log of -1 is j pi. We plug that back into our equation for D, and it simplifies down to this. And this is what you'll find if you search online. And the condition is we set the impedance of our anti-reflection medium to be the product of eta 1 times eta 2. Let's dissect what this equation has told us. That first term, if we take the free space wavelength, divide by refractive index, that ratio is wavelength, whatever the wavelength happens to be inside the medium. We then divide by 4, and this tells us what the length is for a quarter wavelength. And so this anti-reflection layer needs to be a quarter wavelength thick material. This other term says it can be an integer multiple of a half wavelength. So we start off with this quarter wavelength, and we can add on to that integer multiples of half wavelength if we wish to. It may be that somehow we can't manufacture it to be a quarter wavelength, but we could manufacture it to be 3/4 of a wavelength or something like that. So it gives us more freedom. So here's the design procedure. So step 1, we'll choose an anti-reflection material, and we choose it now such that we know the impedances that we want to match between. We calculate their product, take the square root, and that's the impedance of the anti-reflection medium. And by the way, this is actually called the geometric mean, which is different than the arithmetic mean, where we would add these two and divide by 2. This is called the geometric mean. Now, when we do not have a permeability, and most of the time we don't, and we're working with dielectric materials, instead of going through the impedance, we're going to calculate the permittivity as the geometric mean of the permittivities in the surrounding media. Or if we just want to work in terms of refractive index, the refractive index of that middle medium, the anti-reflection slab, is the geometric mean of the refractive indices on either side. So these tend to be our design equations. Once we have the refractive index, or if we have the permittivity, we can then calculate the refractive index. Then we can calculate how thick a quarter wavelength layer is. And this is normally what we do. We go with the quarter wave, but this other term gives us more options. So here's an example. Let's say we want to maximize light through a lens. The lens is made of glass that has a refractive index of 1.2, and the lens is residing in air. We'd like to design an anti-reflection coating that maximizes transmission right in the middle of the visible spectrum, which is about 500 nanometers. Visible goes from about 300 to 700-ish nanometers, so 500 is about in the middle. So step 1. So since we're at optical frequencies, we have a negligible permeability. That means we don't have to go through impedance. We can go immediately with refractive index. And we're given the refractive index in the surrounding media. So we plug in our numbers, calculate the geometric mean, and our anti-reflection layer needs a refractive index of 1.23. The second step then, once we know the refractive index and we know the wavelength where we want this to work, we calculate what a quarter wavelength is. And that ends up being about 101.4 nanometers. Then we can also calculate what a half wavelength is. So our answer can be 101.4 plus integer multiples of 202 nanometers. Well, we can just choose m equals 0 and stick with 101.4 nanometers. And so if we could put a refractive index of 1.23 with a thickness of 1.01 over top of our lens, we would prevent reflections at 500 nanometers. Now that simple design, what we would see as we go away from 500 nanometers, we'd start getting reflections. And in fact, the films that they put on camera lenses have many more layers than just one, so they get a broad band anti-reflection coating. But that's beyond the scope of this class. The very last thing I want to mention, and I won't go into too much details, is something called Bragg gratings, which is more than 2 reflections. It's a series of dielectric slabs, and man, with just one slab, we had an infinite number of waves bouncing around. Now it's even a hugely more complicated arrangements of waves bouncing all over the place. But a Bragg grating is composed of 2 alternating layers. One has high refractive index, and one has a low refractive index. And the length of these layers to get as broad band a reflection as possible is a quarter wavelength. So L1 and L2 are both a quarter wavelength. If we do that, we design as broad band a Bragg grating as possible. And so what happens if we were to simulate this as a function of wavelength, we would get this large stop band. And this is on a dB scale, so this is a very large and deep stop band. And that's what Bragg gratings are very good for. They are band stop filters.